From the previous video, we know that if we have a diagonal matrix with main diagonal entries d1, d2 up to dn raised to the power m, we just have to raise each entry to the power m. In other words, it is easy to compute powers of diagonal matrices. Therefore, it is useful to relate a given matrix A to a diagonal matrix D by A equals P times D times P inverse, where P is an invertible matrix. Then, we may relate powers of A to powers of D using the following proposition. Let A, P, and D be matrices such that A equals P times D times P inverse. Then, A to the power K equals P times D to the power K times P inverse for all positive integers K. The proof of this result is easy by induction. When n equals 1, we need A equals P times D times P inverse, which is given. We assume inductively that A to the power K equals P times D to the power K times P inverse for some positive integer K. Then, A to the power K plus 1 equals A to the power K times A. This equals bracket P times D to the power K times P inverse times bracket P times D times P inverse. By associativity, this equals P times D to the power K times bracket P inverse times P times D times P inverse. Since P inverse times P equals the identity matrix, this equals P times D to the power K times D times P inverse, which equals P times D to the power K plus 1 times P inverse, and this completes the proof. Now, we need to find a way to write A equals P times D times P inverse. To do so, let V1, V2 up to Vn be the columns of P, and D be the diagonal matrix lambda 1, lambda 2 up to lambda n. Then, A equals P times D times P inverse if and only if A times P equals P times D, which is equivalent to A times the matrix V1, V2 up to Vn equals the matrix V1, V2 up to Vn times the diagonal matrix lambda 1, lambda 2 up to lambda n. This in turn means that the matrix A times V1, A times V2 up to A times Vn equals the matrix lambda 1, V1, lambda 2 V2 up to lambda n Vn. Equating the columns, this means that A times Vi equals lambda I times Vi for all I equals 1 to n. This motivates the following definition. Let A be an n by n matrix. A non-zero vector V is called an eigenvector of A if A times V equals lambda times V for some real number lambda. In this case, lambda is called an eigenvalue of A corresponding to the eigenvector V. There are two things to bear in mind. The first one is that any scalar multiple of an eigenvector is also an eigenvector with the same eigenvalue. Indeed, if A times V equals lambda times V, then A times bracket K times V equals lambda times bracket K times V for all real numbers K. Therefore, for a given eigenvalue, we can choose any eigenvector as a representative. The second point is that if A equals C times I for some real number C, then every non-zero vector V in R to the n is an eigenvector of A with eigenvalue C. Indeed, A times V equals bracket C times I times V, which equals C times bracket I times V, which equals C times V, for all V in R to the n. Let's look at an example. Let A be the matrix 3, 2, 2, 0, V be the vector 1, negative 2, and W be the vector 1, 1. A times V equals the matrix 3, 2, 2, 0 times the vector 1, negative 2, which equals the vector negative 1, 2, which equals negative V. Therefore, V is an eigenvector of A with eigenvalue negative 1. A times W equals the matrix 3, 2, 2, 0 times the vector 1, 1. This equals the vector 5, 2, and it is not equal to lambda times 1, 1 for any real number lambda. This implies that W is not an eigenvector of A. In general, to find eigenvectors and eigenvalues of A, we want to find real number lambda and non-zero vector v such that A times v equals lambda times v. It is equivalent to lambda times v minus A times v equals the zero vector. This is equivalent to bracket lambda times I minus A times v equals the zero vector. This is equivalent to requiring that the homogeneous system bracket lambda times I minus A times v equals 0 has a non-trivial solution v. By an equivalent condition of invertibility, this happens if and only if lambda I minus A is non-invertible. This happens if and only if the determinant of lambda I minus A equals 0. This motivates the following definition. Let A be an n by n matrix. The characteristic polynomial of A, denoted by Ca bracket lambda, is defined as the determinant of lambda I minus A. The following theorem summarizes the results we have so far. Let A be an n by n matrix. The eigenvalues of A are the roots of the characteristic polynomial Ca bracket lambda of A. The eigenvectors of A with eigenvalue lambda are the non-trivial solutions of the homogeneous system bracket lambda I minus A times v equals 0. As an example, we want to find the eigenvectors and eigenvalues of the matrix A which has entries 3, 2, 2, 0. Lambda I minus A equals the matrix lambda 0, 0 lambda minus the matrix 3, 2, 2, 0, which equals the matrix lambda minus 3, negative 2, negative 2, lambda. The characteristic polynomial of A is the determinant of this matrix, which equals bracket lambda minus 3 times lambda minus negative 2 times negative 2. This equals lambda squared minus 3 times lambda minus 4, which can be factorized as bracket lambda minus 4 times bracket lambda plus 1. So, the roots are lambda 1 equals 4 and lambda 2 equals negative 1. Notice that the matrix A is the same matrix from the previous example, and lambda 2, which is negative 1, was the eigenvalue that we found before. And now we have found a new one, lambda 1 equals 4. To find the eigenvectors corresponding to lambda 1 equals 4, note that lambda 1 times I minus A equals the matrix 4, 0, 0, 4 minus the matrix 3, 2, 2, 0, which equals the matrix 1, negative 2, negative 2, 1. So we solve the system 1, negative 2, 0, negative 2, 1, 0. The general solution is t times the vector 2, 1, where t is a real number. So an eigenvector is v1 equals 2, 1. To find the eigenvectors corresponding to lambda 2 equals negative 1, note that lambda 2 times I minus A equals the matrix negative 1, 0, 0, negative 1, minus the matrix 3, 2, 2, 0, which equals the matrix negative 4, negative 2, negative 2, negative 1. So we solve the system negative 4, negative 2, 0, negative 2, negative 1, 0. The general solution is s times the vector negative 1, 2, where s is a real number. So an eigenvector is v2 equals the vector negative 1, 2. Notice that this is negative v from the previous example. Let's look at one more example. We want to find the eigenvectors and eigenvalues of A, which is the matrix 1, 1, 0, 1. The characteristic polynomial is the determinant of lambda minus 1, negative 1, 0, lambda minus 1. This equals lambda minus 1 squared. So the only eigenvalue is 1. To find the eigenvectors, we solve the system 0, negative 1, 0, 0, 0, 0. The general solution is t times the vector 1, 0, where t is a real number. So v equals the vector 1, 0 is the only eigenvector of A up to scalar multiples.